Hello sir, my name is Pallav Aneja and I'll be explaining the compiler construction tools. There are many compiler construction tools available to enhance the compiler performance. Some of them are as follows. We'll start with parser generators. These generators produce syntax analyzers, normally from input that is based on a context-free grammar. In old compilers, syntax analysis consumed not only a fraction of the running time of the compiler, but a large fraction of the intellectual effort of writing a compiler. The second are scanner generators. These generators automatically generate lexical analyzers, normally from a specified based on a regular expression. Syntax directed translation engines. These engines produce intermediate code with three addresses format, normally from input that is based on the parse tree. The syntax directed translation engines totally depend on the kind of syntax which you enter into your data. Automatic code generators. It takes a collection of rules that define the translation of each operation of the intermediate language for the target machine. The input specification of the system may contain a description of the lexical and syntactic structure of the given source language, a description of what the output is to be generated for each source language, a description of the target machine. Now, moving on, data flow engines. These are the last type of compiler construction tools which we'll be discussing today. Normally, much more information needed to give a good code optimization involves data flow analysis, the gathering of information about how values are transmitted from one part of a program to each other part. These are the various compiler construction tools which are widely used. Now, moving on, the second part of the question is to solve this grammar for different LL1, LLR0s and other stuff. So this will be explained by my partner Akash Arora.
Hello sir, my name is Akash Arora. As we can see, we have been given this grammar and various production rules associated with it. Now, I will be checking the grammar for LL0, LL1 and LR0. We have various different methods for calculating it. Now we check for LL0. The criteria for the grammar being LL0 is that only one string can be generated. In the example given, it generates two strings as shown. One is S, generates 2, and the 212 operators. Seeing that the two strings are generated, it can be said that the given grammar is not LL0. Now, we check the grammar for LL1. First, we take two cases of X. As it gives us two productions, one of which gives A1B and the second gives 2. We take the first of both A1B and 2. Since first of A1B is A and A points to 2 and first of 2 will be 2 obviously, as it is a terminal. As we can see, intersection of both is not null, and for any grammar to be LL1, we need to have a common intersection point of the first of the values. So it is not LL1. Moving on further. Now we check our grammar for LR0. First, we generate the augmented grammar for the given set of graph and serialize it as we have done earlier, and the method to serialize is as follows. We put a dot in front of S, and since X is pointing after the dot, we find the same serialization for X2. We keep on doing it till we find a terminal at A, or the grammar finishes. Similarly, now we find it for A, as A comes after the dot in the expansion of X, and then X and A both point to 2. Once we have generated all the strings, we name it as group S1. Similarly, we find the augmented grammar using serialization group S2 and S3. But in the third group, we see that we have a conflict, that is reduce conflict, and hence our grammar cannot be LRC.
Now we move on further and check a grammar for LR1. In LR1, the 1 actually signifies the number of look-ahead symbols which we have in our grammar. Now we keep on checking the look-ahead symbol for each and every one of the subparts of the grammar. Then we calculate it. For the first grammar, the first production S has a look-ahead symbol which is actually pointing towards null. Similarly, now we check on for further this. For the second production, the look ahead symbol is pointing towards its perpendicular operator. And for the third production, it's pointing towards the same perpendicular operator, because in the look ahead symbol we have it pointing towards the look ahead symbol. In the fourth operator, it's pointing towards 1. Similarly, we keep on checking it for each and every one of the subparts of this grammar until and unless we reach the rightmost part of the grammar, so that we can calculate whether it's actually LR1 or not. As we can see that all these things are not having any shift reduce conflict or a reduce conflict. We can deduce that the grammar is not LR1. Moving on to SLR1, continuing with LR0 of table C. Here we can see the table C of our grammar. As we can see that we look at the following subsets. We look at the fall of X, fall of A, and fall of this. We can see that fall of X has a perpendicular operator, fall of A has 1 and the perpendicular operator, and the intersection of both these has perpendicular operator. So they do not resolve ambiguity because they have the same operator. So we still have the reduced one. So no, not SLR1. Moving on to LALR1. All the core items in each of the 9 states are different. So no two possible things are to merge, but all core items that are same can be merged. So by default, the grammar is LALR1 because all the states are different.